So in the answer key, he actually did, I guess, well, I don't know. Yeah, he short-circuited a lot of this, you can see. He just said, I already know that this, I already know that this square root is 1/4.
Yeah.
He says, I already know from the previous part that this square root is 1/4, so I'm just gonna plug that in over there. In fact, one thing that we could have done that would have made our life simpler in part A as well is, how would you rewrite this equation in terms of beta?
1 minus beta squared.
So first of all, that would have made our life easier in part A. There was no reason carrying around the v over c term all the time. We might as well just put in beta and solve for beta. And then in the time term, so here's the new equations in terms of beta. And again, this makes it even clearer that they both differ by the same factor, because they both got this same term in them. The relationship between the lengths is in the same ratio as the relationship between the times. Although the ratios are the same, it kind of flips, because in the time equation here, the time measured on the ship was the shorter time, but the length measured on the ship was the bigger length. So you can't assume that just so notice that down here prime referred to the ship, but that does not mean that the prime refers to the ship up here. That's something that's easy to get confused about. The prime in one equation might not refer to the same reference frame as the prime in the other equation. We know here that the rest length is the bigger length, and the rest length is what you would measure from the ship, because when you're on the ship, you feel that you're at rest. So this is something that's confusing about these types of problems. The prime does not necessarily refer to the same reference frame in these two equations over here. So the time on the ship is smaller by a factor of 4, but the length measured on the ship is bigger by a factor of 4. So the ratio is the same, but the relationship between the two things flipped, so to speak. Okay, but the nice thing about this problem is you didn't have to worry about all of that. You never have to have learned about all the relativity stuff we went over. You could get both of these problems right just by keeping track of mathematically which of these has to be the smaller variable over here. So at least on this problem, he was not testing deep insights into relativity. He was just testing mathematical facility with this equation. Well, this is what we emphasized when we did the homework on this. We emphasized focusing on which of these variables is bigger and which is smaller.
So the pictures are just to find out which one's bigger.
Yeah, well, the point is, this problem, we didn't need the pictures because he gave us so much information. He told us which was bigger and which is smaller. That's right. The pictures, because remember that what we know that the shorter length is the length measured, the shorter length is for the observer to whom the 2 points appear to be moving.
Yeah.
And the shorter time is measured by the observer to whom the two events appear to be in the same place. Yeah. And it's only by drawing the pictures sometimes that we can tell whether the 2 points appear to be moving or the two events appear to be in the same place. In this case, though, we didn't need all those pictures because the problem just put right into our lap, which was the smaller one. But you can see why the rest length is always the bigger one. The rest length is the length measured by the observer to whom the points appear to be at rest. The rest length is the length measured by the observer to whom the points appear to be at rest. Well, we just said that the length appears shorter when the points appear to be moving. So actually, you don't have time to do a whole other problem, so let's just get that nailed down for this problem. Alright, so this is what we said before. The measured length is shorter between 2 points for the observer from whom the 2 points appear to be moving. And we know from just looking at the mathematics of the equation that L prime has to represent that shorter length. So when the observer from whom the 2 points appear to be moving is the one that measures L prime. Okay, so in this particular case, what were the 2 points?
The spaceship.
They were the 2 ends of the spaceship. So the 2 points were the tail end of the spaceship and the front end of the spaceship. Okay, and then we had 2 observers. We had one observer who's on the spaceship, and we have another observer who's outside the spaceship. Well, to which of these observers do the points appear to be moving?
Outside.
Yeah, to this point, it appears to be moving. The guy on the ground. So this is the guy that gets the shorter measured length L prime, and to this guy the points appear at rest, right? To this guy the points appear at rest because he's moving along with it. Remember, an observer always assumes that he's at rest. The guy in the spaceship assumes that the spaceship's at rest, and then the ends of the spaceship appear to be at rest, so he's the one that measures the rest length. The rest length is the distance between 2 points measured by an observer to whom the 2 points appear to be at rest. The rest length is the distance between 2 points measured by an observer to whom the 2 points appear to be at rest. Well, when you're on the spaceship appears to be at rest. So that's the rest length. So as we already said, this represented the distance measured on the ship, and this represented the one measured on the ground, and that would prove to us that the rest length is the longer length.
Yeah.
We didn't have to figure that out here because they told us that the rest length was the longer length, but if they hadn't told us, we could figure that out from here. The rest length is always the longer length. Okay, and then how about for the times? Measured time between 2 events appears shorter for the observer for whom the 2 events occur in the same place. So then the 2 events could be, you can pick any 2 events that happen on the spaceship. So we could say that the first event is the guy on the ship wakes up, and the second event is the guy on the ship goes to bed. You can pick any 2 events that are happening on the spaceship. Now, to which observer do those events appear to occur in the same place? The guy on the ship or the guy on the ground?
Yeah, ship.
So that's the T prime guy. The guy who measures T prime is the guy for whom the 2 events appear to occur in the same place. Well, if you're on the ship, when you get up is the same place as when you go to bed. They're both on the ship. So the ship here represents T prime, and the ground represents T. Now we know that T prime is the shorter time, which means that your clock is running slow. If you're measuring less time, you could interpret that as the clock running slower. And the guy on the ground is going to measure more time. Or you could interpret that as the clock running faster.